Okay, we're in section 26, this is parametric equations. These notes pretty much are verbatim what I give to my Math 120 students. So this material has been covered before. However, for whatever reason, our division says we need to review what you learned in Math 120. All right, so we're going to review it, but we're going to tack on some new material. Particularly, what we're going to tack on is the calculus of the parametric equations. Basically the first and second derivative. All right. So the bottom line is, I'm a big fan of technology. And the reason for that is that, my graphs, no matter how good I think I could draw, I really can't draw a very good graph. And this is so true. I mean, it's almost like saying that, when I write things down, I can certainly write with write things down, but it's hard to sometimes read what I've written down, even by myself. And this is why I've learned to type. And you should also learn to type. All right, I kid you not. No one's going to look at your chicken scratch and say, gee whiz, I like what you're doing. They want to see things typed up and presented. That's what we do with the notes, by the way. And certainly we're trying to lead by example. We'd like you to be able to do this as well. So let's go back to the graphing. Graphing stuff, there's no doubt about it. Simple things, though, you should do simple things by hand. All right. If it gets to be a long, complex problem, you want to learn how to use technology. Just like these notes. I mean, these notes are, almost 500 pages long. And by the way, I did do a lot of paperwork to write these notes, by the way. I used a tremendous amount of paper and pencil to do the notes, but I had to type them up, all right? They get long. So when things get difficult, you're going to be using technology to help you out with that and help you out with the presentation of it. And this is true when we're doing graphs. So, those simple graphs, eventually we get to more complicated graphs, but for the most part, we'll talk about it. Right. And we'll talk about one step at a time through these problems over here. Yeah, this might be tedious. It might be, this is a repeat of what I did in Math 120. And it is a repeat. There's no doubt about it. I will talk about using software and I'll try to keep it simple. All right. What do I mean by simple? For those students that do not want to use what I'm asking you to use, which is Sage and Grapher, you can use Wolfram Alpha or any other application you want. And this is a godsend. And I'll tell you why. You're going to end up at places like NJIT, at least most students do, where they mandate the software that you need to use. They don't leave it open to option. They say everyone's using this particular piece of software, right? I think that's bad, by the way. It's sort of like, it creates an environment where things must be done on their application. And their application of choice, at least in the past, I'm not sure what it is today, is MATLAB. All right. My suspicion, the reason for MATLAB gave them a good contract. They're paying for it, though. I'll tell you that. MATLAB's not free software. So they're paying for it. So I'm going to say, yeah, you can see me doing software, but you'll see me work through this stuff over here. I know it's difficult. All right. We want to encourage you to give it a try, though. All right. We'll eventually get to examples. Yeah, the examples, some of those are going to be tedious, too. Enough to give me a headache for examples, particularly with the graphing. So I'm going to go back to the whiteboard and we'll start the lecture part of it. Okay. So, and again, I'll mention software as I go through the lecture. So let me go a new share. All right. So let's talk about it. And, first thing up, parametric equations. And what we're going to do is, parametric equations, we're basically saying, X is a function of T. I'll put this over here for you. I don't know what it is, a function of T, by the way. And I'm going to say Y is also a function of T. I don't know what it is. All right. So what I start off with, I'm really not starting off with a parametric equation. I'm starting off with a problem that I find difficult to deal with, but it's not terribly difficult. I mean, the machine can do it. And I'm going to say, I'm looking at this one, which is not written as a parametric problem. It's not written as X is a function of T or Y is a function of T. It's just simply written down as a relationship between X and Y. By the way, clearly not a functional relationship. But if I were looking at this graph over here and someone said, hey, that's a graph, and I'm looking at that graph of this relationship, and there's a red tangent line over there, I'm going to say, yeah, I can see that. I can see the red tangent line. And I'm going to say, I kind of see that right over here. I see the tangent line. All right. So someone says, well, who drew that? I didn't draw that. A machine drew that. All right. I had to tell the machine how to do it, though. I'm not going to say it's difficult to do. You just do that. You have to say machine, draw this picture for me. And it's a relationship It's pretty easy to type in, by the way. All right. So I'm going to say, kind of looking at it, I think a machine could do that. And then the question becomes could I come up with the equation of that tangent line? Here's my problem, by the way. If this were given to me without a picture, and they said, find the equation of tangent line where x is less than 1, but greater than 0, and y is less than 1, greater than 0, I'd have a tough time. I would say I need to get a visual of it. And this visual here is helping me a great deal. So what I want to do is I want to talk about how to get the equation of tangent line, and I got the picture. So what I want to do is over here, I want to write this down for you. Again, I'm hoping this is not much of a struggle for you. And again, we're in the land of calculus now. I'm going to write this over here. Y times sine x squared minus y squared equals x times cosine x plus y. Now here's my problem. And someone says, well, yeah, I don't know what your problem. I have no idea what this is going towards. I'm looking at it. I'm kind of going to zoom in over here. And I'm thinking to myself is, if they're asking me the question, this has got to be an easy number here. So I'm looking at it. This is a trig problem, right? So I'm wondering, what would be an easy trig number there between 0 and 1? I start thinking about it. So I know it's a decimal number like 0.7 or something, 0.8. So I'm saying, what trig number is around 0.7, 0.8? I'm going to just think, just simply say, I don't know, maybe x is pi over 4. Maybe I'm wrong, by the way. I don't know. Maybe it's like a really bizarre number. And then I'm going to say, it looks like the y is the same number. I don't know if that's true, by the way. Let me go over here. I'm going to plug this in. So I said x and y are equal, and I said x equals y equals pi over 4. So I'm going to write this down. Pi over 4 times, it's going to be tough, sine, pi over 4 squared, right? That's going to be pi squared over 16 minus pi squared over 16 equals, what's x? Pi over 4 cosine pi over 4 plus pi over 4. Gee, this doesn't look good. What do you get over here? Pi over 4 times the sine, that's 0, right? Pi over 4 cosine, that'd be pi over 2, right? What's sine of 0? 0. What's pi over 4 times 0? 0. Pi over 4, what's cosine of pi over 2? 0. This worked. It's a miracle. Not really. We really do write problems where there are no miracles. So I know this point conclusively. And what is this point? It's pi over 4, comma, pi over 4. Now, what do I want to do? I want to get the equation of the tangent line. And I'm going to say that should be relatively simple looking at that picture. What's it going to be? Y minus pi over 4 m tangent x minus pi over 4. I get a problem though. And my problem is, what's that tangent line slope? That's really tough looking. I don't know if I could do that. What I do know about it, I do know the m tangent is positive. And I want to point out in the past what you might have done in like Math 100 is drew a triangle in there and ballparked it. And if I were to ballpark that, I would say the slope of the tangent, whoops, I keep doing that. The slope of the tangent, roughly speaking, looks, I don't know, one, I don't know, maybe roughly, I'm struggling. I'm gonna say 1, maybe 4, roughly 4. Looking at that picture, it's rough, right? Roughly 4. That's not good enough. I gotta do the work. So what's the work? I must find out. I'll write this over here. I must find out what dy dx is at the point pi over 4, comma pi over 4. I know I have to find that out. Why is that? That's m tangent. So how do I do that? And I'm not saying it's going to be easy for you. I got to differentiate this guy. How do you do that? Implicit differentiation. Let's write this down. So I'm going to say the derivative of y is dy dx. I'll write that down for you. Times the sine x squared minus y squared. Boy, it's going to be tough. Plus, right? Hope you realize what we're doing now. It's going to be y times the derivative of sine, which is cosine, x squared minus y squared. This is going to go on forever, by the way, times the derivative of the inside, which is 2x dx dx minus 2y dy dx. Wow, that was a lot of work. Equals, you see how long that is? Let's do the other side now. Derivative of x is 1 times cosine x plus y minus x sine x plus y times the derivative of the inside, which would be 1 plus dy dx. That's a lot of work, wasn't it? Now, what do I want to find out? I want to find out what dy dx is when x and y are pi over 4. Let me write this down for you. So I'm going to take this thing here, and I'm going to try to figure out what dy dx is when I get the point pi over 4, comma pi over 4. So what do you get? Dy dx. It's tough. I'm not saying otherwise. Let's see. You get sine of 0, right? I got that done. Let's go to the next one. Pi over 4. And what's that going to be? Well, that's going to be cosine of 0. I think I can handle it. Times 2 times pi over 4, which is pi over 2, minus 2 times pi over 4, which is pi over 2, dy dx. It's tough. I'm going to keep going through it, though. Equals, well, let's try track of this. It's going to be 1 times the cosine of pi over 2 minus pi over 4 times the sine. Well, that's going to be pi over 2 now. Times 1 plus dy dx. I think you can appreciate how difficult this is. Let's see, what's sine of 0? 0. What's cosine of 0? 1. So let's write this down. Get pi over 4. Pi over 2. Minus pi over 2. Dy dx. Things are getting smaller. What's cosine of pi over 2? 0. What do you get? Minus pi over 4 times sine of pi over 2. That's going to be 1. 1 plus dy dx. It is work. What's this going to be? I'm going to write it down for you. Pi squared. 4 times 2 is 8. Minus pi squared over 8 dy dx. Minus pi over 4. Minus pi over 4 dy dx. I can multiply both sides by 8. Pi squared minus pi squared dy dx equals minus 2 pi dy dx. Whoa, this is going nowhere. No, it's not. It's going somewhere. So what are you going to do? Pi squared, let's see, plus 2 pi. I'm just taking those two terms over there. And then you can get pi squared dy dx minus 2 pi dy dx. Let's keep going. Pi squared plus 2 pi equals, well, let's see, what do you get over there? Pi squared minus 2 pi dy dx. Let's keep going. Pi squared plus 2 pi divided by pi squared, whoops, minus 2 pi equals dy dx. Well, it's pretty difficult, doesn't it? I'm going to divide by pi plus 2 over pi minus 2. That's my slope, right? What's that approximately equal to? Well, if I look at it, I'm going to say in the 4 range. All right, I didn't do the comment. I'm just saying it's in the 4 range. All right. So let me see if I got it right. How will that work? It's crazy, isn't it? Go back over. I know it's a lot of work. Pi plus 2, pi minus 2. Oh boy. Hope I'm not making you different. Yeah, we did okay. We did it right. Got it right over here. By the way, this is tough. A lot of students break down in that. We're not asking to break down in that. We're asking to persevere and go forward on it. All right. So someone says, what helped me the most in that problem? Prior knowledge, how to take a partial derivative, but also, my knowledge of trigonometry, looking at a nice picture, yada, yada, yada. How did I get that picture? I use Grapher. All right. So that's an introduction. What's the introduction to? You really do need accurate pictures. All right. Now, when I put my chicken scratch down, they're not terribly accurate pictures, but we need an accurate picture. We really need an accurate picture. The next page I want to point out is when I start introducing parameters. These are identical notes to what I give my students in Math 120, identical. So over here, I want to point out, we take the familiar and we start making it unfamiliar. We start to say X is related to a function of time, or T, it doesn't have to be time, by the way, and Y is a function of time. So as an example, this one over here couldn't get easier. I know exactly what that looks like. But then when they do something like this, and someone says, can you do that? That's when things get really tough for students. So what I'm going to recommend you do, when you see the unfamiliar, try to make it familiar. Let me write this down. X equals 2t and y equals 4t plus 3. What's making this look unfamiliar to me is there's a t in the problem. So what I want to do is I want to eliminate the t. I need to go back to familiar territory, eliminate the t. How am I going to do that? There's a variety of ways of doing that. But one thing I would do is suggest solve one of those equations for t. I'm going to take the x over 2, and that's t. I took the first equation and I solved for t. Then I plug it into the second equation. And what do you get? Y equals 4. What's t? X over 2 plus 3. What does this give me? Y equals 2x plus 3. This should be familiar to you. This and this graph out is the same. So I'm going to say elimination of parameter is not a bad idea. However, it can be deceiving. All right, so what I want to do is I want to talk about the relationship between the two now. All right, so we're going to look at the graphs, and the relationship is, if you graph this one out over here, it says the graph of y equals 2x plus 3. I graphed it out. I did an image of my software over there. And then I also graphed out the parametric one. Now, are they identical? They are. So I want to point out, doing the parametric one, and let me see if I can remember. Whoops, sorry about that. I did it again. What's the parametric form? X equals 2t and y was equal to 4t plus 3. I want to go back over here and point out, I did that right. And then over here, this is y equals 2x plus 3. I want to point out, if I were graphing this by hand, super simple. You'd have a y-intercept of 3 and a slope of 2. I'm going to just say rough ballpark like it's over here. That's the graph that I was doing it by hand. Is it as good as a machine does? No. This is the problem for a lot of students doing this over here. What they end up doing is thuggery. I want to point out the thuggery is tables, not a good idea. However, it does work. They take a t, then they write down what x is and what y is. What are easy t's to choose? I'll point out to you, an easy t to choose would probably be 0. And this is thuggery. If I chose 0, what would you get for x? 0. I'm just going to do x first. And then I take 1, you get 2. Then I could take 2, I get 4. Then I take 3, I get 6. That's pretty easy. Minus 1, minus 2, minus 2, minus 4. All right, then what do you get? Well, let's do the y's now. Well, if you took the y to be, the t to be 0, again, I'm selecting on the t, the y would be 3. If I did 1, I get 7. If I did 2, 8, 9, 10, 11. If I did 3, 12, plus 3 is 15. I think you get the idea. Minus 1, you get 4, minus 4 plus 3, which is minus 1, minus 2, minus 8, minus 5. And then you plot these points over here. Every single point you plot. You should start to realize after you plot those points, you're going to end up with the same exact line. All right. By the way, our graphs are done on a Cartesian plane, x and y. All right, you get the same picture. So tables, thuggery, but it does work. All right. What do I talk about over here? Another problem. So the way they're written down, typically in most textbooks, is they're written as an ordered pair of numbers. So to say, given the parametric curve, I'll write this down for you. And they say x is a function of t. I'm sorry about that. I didn't say x is t. X is a function of t. And what is that function? It's given to me. It says it's 2t minus 4. And they say y is also a function of t. I'm going to call it g now. Just don't call it f. That's a different function. It's 3 plus t squared. All right. So what I'm going to do over here is, I'm going to say, I don't want to go to tables. However, I'm not opposed to it. Tables, fine. Let me write this down. X equals 2t minus 4 and y equals 3 plus t squared. I want to eliminate the parameter because parameters are unfamiliar to me. Which equation is easy to solve for t? That first equation. So what do you get? X plus 4 over 2 is equal to t. And then I pop it in here. And I want to tell you what we get. Hopefully something familiar, by the way. Not always, by the way. You get y equals 3 plus t squared. What's t? X plus 4 over 2 squared. All right, let's write this down now. What do you get? Y equals 3 plus x squared plus, let's see, that would be 8x, right? Plus 16 over 4. Oh boy, I got to do more work now, don't I? Y equals 4 x squared plus 8x plus 16 plus 12 plus 28. All right. What do I know about this guy over here? It's a, let me write down a little different than this. 1/4 x squared plus 2x plus 7 is an equation of a parabola. Let me graph it out for you. By the way, I'm not saying my graphs are good. Don't think that for a second. So let me get the vertex. Okay, so minus b, that's minus 2, over twice the a, that's a half. So that's going to be minus 4. I'm getting the vertex down first. Let me get the y value now. So that's going to be 4 minus 8 plus 7. That's going to be 3, right? So minus 4, 3. 1, 2, 3, 4. And how's this problem open up? Upward, like this over here. That's my rough picture. I'm done. All right, but I'm done, but maybe I've got it wrong. Who knows? So They didn't even ask for graph it. They said parametric equation. Let's see if I got that right. I did a lot of extra work, but that can't hurt. I did this over here. Okay, so that's not so bad. All right, let's keep going. And, so this one, they give you the parametric. It says verify table 1 is correct. Well, I'm going to go to table 1 now. I'm going to the next page. It says I won't bore you with the details, but everyone needs to do this. I'll tell you what you need to do. I want to point out here, they told me that the t's, I'll write this over here. They said the t's were between -3 and 3. All right. They want me to verify the table, by the way. And so it's a lot of work. Not really. So I want to point out what I did. I like to go in order for the t's. So this is the t column. They want to verify this. Now, looking at it, what do they got? They look like they start at -3, and that seems reasonable to me. That's where they're starting. Now, by the way, so what's the next number? There is no next number, but the next number for me is the easy number for me, which is -2. Then they go to -1, then they go to 0, then they go to 1, then they go to 2, then they go to 3. Then what do? They want to verify the table's correct for the x. And they want to verify the table's correct for the y. I think y is easier to do first. And why is that? It's just twice the value of t. So if t is -3, I get -6. If t is -2, I get -4. Relatively simplified. If t is -1, I would get y is -2. So forth and so on. I hope that's not difficult. I got to tell you, though, for a lot of students, mistakes happen. Myself included, by the way. So I'm going to look at this in easy values for x. 0 for t. I would say -1. What would I get? I would get 2 minus 1, which is 1. I would say 1 is easy for me. That would be 2 plus 1 is 3. Then I'd probably say 2 is easy. That's going to be 2 times 2 is 4, times 2 is 8, 10. I would say -2 might be easy. What is that going to give me? 8 minus 2 is 6. Then I'd probably say 3 is easy. 9 times 2 is 18. 18 plus 3 is 21. Fairly simple. -3. That's going to be 9 times 2 is 18. 18 minus 3 is 15. You need to be able to do this. I can't say this enough times to you. You need to be able to verify simple tables. Then what do they tell you to do? Plot the points in order. I am going to do 1 point at a time. I am going to do this point here. It says x is 15, y is -6. Done. They say plot this point. That's 6 minus 4. Yes, we provide these pictures for a reason. To speed the process up, by the way. 1 minus 2. I think you're getting the idea that points are being put down. 0, 0. 3, 2. 10, 4. 21, 6. Okay. I plotted all the points in order. Now I'm going to take this over here and I want to point out this thing has a direction of movement. And let me go through that with you. We started here. This is the first point. Then we got to the second point. We're going in this direction. Then what happens? We're still going that direction. And here's the problem for a lot of students. They're looking at this and wondering what's happening over here. It's still going in this direction, but I want to point out what's happening now. It's starting to move not from right to left now. It's going from left to right now. I think you get the idea what I'm doing over here. I'm connecting. This is the start. And this is the stop. Okay. So let me look at this. It does this over here. I want to get across to you that what's nice about parametric problems is they're going in a direction. Let me just go over here. We're starting here. What's it doing? The x's are moving to the left. then they stop over here and change direction, and the x's are moving to the right. Let's talk about the y's. What are the y's doing? The y's are always moving upward. Okay, we got our picture done. All right, let me go back and just give me 1 second. I'm going to just talk about this over here. And oh boy, number 3. Number 3 says, try to make sense. I made a mistake. I'm sorry. And let me just see if I can do that again. I want to see if I can make sense. And again, they're introducing concepts here that I may not be terribly familiar to you. I mean, if you took Math 120 and you say, I can't remember anything I've done there, it's an unfamiliar territory. But let me write this down for you. And what is x? X is what? Is 2t squared plus t. And what do they tell me in number 3? They say, you know, differentiate them and see if you make sense out of these derivatives over here. So what's dx dt? It's 4t plus 1. All right, let's write y down. Well, y, I can't remember, by the way, is 2t. What's dy dt? It's 2. By the way, what does this really tell me? It's easy to understand. This is always greater than 0. So what does it say? Dy dt is positive. It's always moving up. Now, what's this one over here saying? Well, dx dt is the left to right motion. So what I want to do is, when does it equal 0? It equals 0 at minus 1/4. All right. I didn't mean to put the arrow there, sorry. Pick a number after minus 1/4, plug it in, like 0. What do you get? Positive. What does that mean? Moving up. If you took a number to the left of minus 1/4, what would you get? It's negative, which means it's moving. By the way, I'm sorry, I said up. I'm confused. I'll even make the writing better. Give me 1 second. Moving to the right. I'm positive, right? We're doing the x direction now. And this one's going to be negative, which means it's moving to the left. All right. Let's go back to our picture and see if we can make sense out of that. What do we say? The y's are always moving up. Always moving up. But what did we say? We said in the negative motion, right? That minus time. What happens over here? And I'll point this out to you. At this point over here, this would be t equals minus 1/4. That's the vertex of that, by the way. What are we saying? This thing is moving to the left. What hits the time, minus 1/4, it starts moving to the right. All right. Try to make sense out of that. All right, let's go to the next thing up. We made sense out of the derivatives, and this is all written down for you. Let's go to the next page. The next page is eliminate the parameter. All right. So I hate to tell you, I can't remember sometimes, but I'm gonna select this guy over here, and I'm gonna eliminate the parameter over here. And there's a problem with it, but we'll talk about it. I'll put this on the side. Okay, let's write this down. So x equals 2t squared plus t, and y is equal to 2t. If you limit the parameter, I would say probably solve y for t. And what do you get? You get y over 2 equals t, and then plug it in over here and see what you get. You get x equals 2 times y over 2 squared plus y over 2. I got to do this. What do you get over here? You would get y squared over 2 plus y over 2. I don't know, maybe I'll just do this. 2x equals y squared plus y. I definitely notice the problem, by the way, it opens like this over here. And therein lies the problem, by the way. A lot of people think that's what that graph is. It's not. The graph is only between -3 and 3. And that's why it's so important you look back over what we just did. All right. But anyway, this elimination parameter, I'm pretty sure we got that. Did we get it? Yeah, we got that. All right. You should also see the graph and the relationship between x and y may differ, as in the example that we just presented to you. Let me just go over that again with you. If you look at this picture over here, the graph of the parametric was this little red portion of it. The graph of that parabola actually goes on forever, by the way, and that's a problem. So it brings us to this section over here where people become easily tricked. We are not here to trick anyone. All right. Someone says, well, why do you say we're easily tricked? It's true. Humans are easily deceived. Right? They're easily deceived. That's what people like about trickery, that they're easily deceived. They're often shocked when they're deceived. All right. So what I want to do is I want to look at the problem and talk about why people get tricked. All right. So the reason they get tricked is they're always looking for an easy way out. And what do I see? I see x equals cosine of t, and I see y equals the sine squared. Now, I think you probably know at this point, I'm confused by parameters. So what I would do is saying, I don't like those parameters. Confused by, it's almost like, you're confused by something, you get rid of it. I'm going to get rid of it. And the way I'm going to do that, I'm going to see, I think I see it. I think I see x squared, I'm squaring both sides, cosine squared t. This is a typical trick, by the way. Trick you learned in Math 120. Because 120 is all about trig. You're going to add these two together. You get x squared plus y, and then you get cosine squared t plus sine squared. Hope I didn't do too fast in that one. X squared plus y is equal to 1. Well, that's easy. What do you get up here? Y equals 1 minus x squared. Man, that's familiar. I know exactly what that looks like. What does that look like? It's a parabola that looks just like this. It has a vertex at 0, 1, 2 x-intercepts, -1, 0, -1, 0. And then I hand it into the teacher, and the teacher says, it's wrong. Let's talk about why you got tricked. So I'm going to say, you did a great job. You eliminated the parameter, but you got tricked. How'd you get tricked? What I'm going to recommend over here, looking at the problem, is realize that the x value, looking at this, just looking at this over here, the x must be between -1 and 1. Now, why is that? The cosine function is never going to exceed 1, and it's never going to go below -1. Now, the y is never going to exceed 1. All right, I'm seeing a sine function here. This is squared, though. That means it's never, ever going to go below 0. So then the question is, what does the real picture look like? Well, the real picture over here looks like, it still looks like the parabola, by the way, but it looks like this over here. That the x's are going to be between -1 and 1, and the y's are going to be between 0 and 1. That's what it's going to look like. So it's only a part of this thing. It's only this part over here. That's the only part of it is. All right. So people get tricked. So I'm going to say, I don't like being tricked. I get tricked all the time. Actually, I do enjoy getting tricked. I love magic. All right. I hate to tell you, the school's not magic, though. It's kind of mundane. All right. But anyway, you give you the picture of it. Let's talk about using software next. All right. So I'm going to talk about historically what we used at Essex County College. I was big on promoting a product called Mathematica. I'll outline this for you. And I was really big on it. I mean, I asked the school to go out and buy the license. I would write notes, I'd write books, I'd write courses, and I spent a lot of time on promoting it. I'd have seminars, I'd give faculty seminars, student seminars. We actually created a course called the M10 course. It was a 1 credit course. I couldn't get the school to give credit for it, but we had a bunch of students register for the course. And one of our professors, Professor Yee, said, since the students weren't getting credit, you'd have to motivate them to do it. So he actually said, if you complete the course, if Ron Bannon says you complete this M10 course, he'd give them money. And he gave them money, right? Very generous. He gave them money. Each of the students, and how many students finished it? I'm going to say maybe, I don't know, maybe about 10 students. So anyway, I designed this complete course on getting students to use Mathematica. And, certainly they could do simple things like this. We'll talk about that in a second, by the way. That's code, by the way. By the way, the school paid for the software. I'm going to say, I can't remember offhand, but I'm going to ballpark the number, maybe for 5 years, 10 years, I don't know. But they were spending a fortune on the license. I mean, an absolute fortune. I mean, it's tens of thousands of dollars. And then they asked them to do an audit on it. And what they found out was that even though Ron Bannon was promoting this to no end, spending an inordinate amount of time writing notes, courses, guidebooks, that the only person ended up really using it, none of the faculty were using it, none of the students were using it, no one was using it except for me. So that's when they canceled the software. They said, we're not going to pay for this. Outrageous. The students aren't using it. It's like having a library where no one goes to it. I had to tell you something. That's going to happen to libraries in many communities because the community does not support the library. All right. So Mathematica is gone. But anyway, let's go for the talk. Right. We'll talk about me doing Sage and Grapher. So I'm going to say this is the picture. And I want to tell you, if I were looking at this over here, there is no way I could do this. All right. So I'm going to say software is a nice thing to have. And let me go over that. And what's X going to be equal to? X is going to be equal to cosine of 3t. And what I know about this over here, if I were just, saying, graphing it, I know the X, again, is between -1 and 1. How do I know that? The cosine curve never bounces out of that. Now, what's the Y equal to? It's cosine of t. This is really crazy, right? Cosine of 3t. What do I know about the Y? The Y is between -1 and 1 as well. So if you look at the picture, I want to point out what I mean by the picture. The picture is going to fall between -1 and 1 and 1 and 1. But I got to be honest with you, I'd have a really tough time drawing that picture. The only thing I could really tell you about that picture is I could tell you that picture fits in a box between -1 and 1 along the x-axis and -1 and 1 along the y-axis. But all I could do, I definitely need to use software. We are going to recommend that you also learn to use software. Again, I know my talk about Mathematica may have fell on deaf ears. Mathematica is no longer available to you. It's a great software. It's used in industrial applications. Certainly a lot of companies have it. And it's a really good software. The software that I would recommend you do is, Sage or Grapher or Wolfram Alpha, whatever you're comfortable using, but you'll be able to do that. Pretty easy to do. All right. So what I'm going to do over here, go to the next page and just simply talk about going to the calculus now. All right. So the calculus, a little more complicated, but I want to point out to you, looking at these things over here, I really think I could do the derivatives of these things over here, with the exception of the second derivative. So I'm going to write this down for you. That's x equals t cubed. And I'm going to write down y. And what's y equal to? Y is equal to, whoops, I'm sorry, I put an equal sign that doesn't belong there. And the y is equal to 2t minus t squared. And I think you know that I'm unfamiliar with the parametric, so I need to get myself familiarized with this. And I want derivatives. So what derivatives do I know? I definitely know dy dx. All right. So what I would probably do is try to solve this thing to get rid of the t, elimination of parameter. And I'm going to say the first equation, I'm going to say x to the 1/3 power is equal to t. And then I'd plug it in over here. What do you get? You would y equals 2 t to the 1/3 power. I'm not sure. I'm sorry. I must be sleeping. X to the 1/3 power minus, well, now the t is being squared, so x to the 2/3. Now I can write my derivative down. What's dy dx? Fairly simple. It's going to be 2/3 x minus, did I say that right? Oh, minus 2/3, right? Minus 2/3 x, I got to take 1 away right now, minus 1/3. So I found the derivative. But I gotta be honest with you, I'm not opposed to that. I'm not opposed to that. And I have that written over here. That's going to be, you know something, I think I wrote something down wrong there. Oh, I'm sorry. I didn't write something down wrong. I'm just writing down the this over here. I'm sorry about that. Make sure I wrote that down. And then a derivative. Did I do the derivative? Let me check. -4, 2/3 x to the minus 2/3. Yep. Let me do that. I'm looking at this over here. And then 2/3, 1/3. I did it right. Okay. So I did all that business over there. But we can't always do this. And I'll tell you the reason we can't do it. Sometimes eliminating a parameter is absolutely impossible. So what I want to write down, I want to write down another way of doing it. So I'm going to say eliminate parameter is not a bad idea, but most times we can't do it. So let's do it a little differently. I'm going to write this over here, x equals t cubed. And I'm going to say x is a function of t. I've seen it clearly. And y is a function of t. And what is it going to be? It's 2t minus t squared. And what I'm going to write down is I'm going to write down dx dt. I can do that pretty easily, by the way. That's 3t squared. And then I'm going to write down dy dt. And what's that going to be? That's going to be 2 minus 2t. Did I do that right? Yeah. Then I'm going to write down, I don't want those. What I want is I want dy dx. The way I'm going to do that is write down dy dt over dx dt. And what does that give me? Well, let me write that down for you. 2 minus 2t over 3t squared. Did I do that right? Yeah. So what does this give you? I'm not sure I could do it. Maybe I could factor 2 out. 1 minus t and 3t squared. So I got the derivative. What's the difference though? This over here just involves x's. This one involves t over here. All right. You might be confused at this point. I realize that. So let's see if we've done that. I think I've done that. And let's go to the next page. I got this down. This is going to be the tough part. I'll read through it for it though. All right. So, x is a function of t. Y is a function of t. But I'm using f and g with the functional notation. I'm going to say the relationship between x and y may not be explicitly known. Okay, I'm just going to use the big letter F there. What's the big F? It's g of t. That's a substitution, by the way. What's x? It's f of t. I got that part written down. I'm just reading through the work, by the way. And it's tough. I'm not saying it's easy for you. Don't get me wrong there. And then I'm looking at this over here. This is one way I would remember this. This is all about getting a second derivative, by the way. So I'm taking a derivative, right? That means chain rule, right? So there's going to be g prime. There will be dt dt, which is 1. This would be big F prime. Evaluate ft times the derivative of the inside. That's pretty simple. And then I get this, this big F is equal to g prime over f prime. Well, you know what? I think I found out what I wanted to find out, which was dy dx. And that's the derivation of what we just did. All right. So I did that. That's not bad. We found out something over here. Found out what probably we knew intuitively. And that's not a bad thing. Here comes a tough one. Second derivative. I'm sure you've seen me do that before. And what are we really doing over there? We're doing this. That's a second derivative. Let me look at that. Yeah, we're taking the derivative of y with respect to x. We're differentiating with respect to t on that one over dx dt, second derivative. Whoa, 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 whoa. I got to write that down now. So I think we did this before. Do you remember? Now I want to see if I can do this. By the way, we did this on the prior page. All right. I want to see if I get the second derivative though. I want to see if I can do d2y dx squared. All right. What goes on bottom? Dx dt. You know what? I can't even remember. I got to go to the next page. I got to copy these things down. I know it's tough. All right, let me just quickly go through this with you, all right? So I'm going to say, I think I can get dx dt, right? Yeah, dx dt. Yes, it's a repetition of what we just did. That doesn't look right. I think I write down dy dt. And I think I can put down dy dx now. What's it going to be? 2 minus 2t. We just derived that form over there, by the way. 3t squared. That's not so bad. And now I get the second. Second, I always find it difficult, to be honest with you. So what do I got to do? I got to do dx dt. Did I do dx dt? Yeah, it's 3t squared. I just did this thing over here. I just did it. I don't do that again. But did I do this? I don't think so. Let me write that down. D dt. And what's dy dx? What's this business over here? It's not going to be easy, by the way. It's going to be work. Painful too. I'm going to write this on the side though, because I don't want to do a lot of work over here. I don't want to use quotient rule, so I'm going to write this a little differently. All right, that's my preference, by the way. It may not be your preference, but that's okay. That's going to be minus 4 thirds t minus 3. We'll check with the key, don't worry. Plus 2 thirds t to the minus 2. I don't like the way that looks. I'm going to write a little bit differently. I'm going to write it as minus 4 thirds t cubed plus 2 over 3t squared. I'm divided by 3t squared. I make mistakes sometimes. We'll look at the key later. Minus 4 over 9 t5 plus 2 over 3 t4. I know, I'm sorry, not, I made a mistake there. I'm gonna get my eraser out. You can make mistakes too, by the way. Certainly, all I'm saying is I'm not even looking at the key yet. I'll get there. I'm gonna say 9t5, right? So what do you get over there? 2t minus 4. I don't know. Might have made a mistake. Let's take a look. Let's see if I got that. And wow, I think I got it. All right. By the way, they also do the dy dx. You can do that if you want. I'm not suggesting you do that. All right. So let me just make sure I did get that. 2t minus 4 over 9t5. We did all right. All right. We did it right. So I'm going to summarize this over here, that we know how to take a derivative dy dx. Fairly simple. It's this over here. The second is a little more complicated, but we can do that. All right. So let's keep reading. And again, I know it's difficult. And what I want to claim over here is it's nice to have pictures. And we have the picture of this over here. And, kind of looking at it, there's things I know about it. And looking at the picture over here, it's a partial picture, by the way. looking at the picture, again, what I mean by that, I see that, I see part of it. I see it looks like this over here. Again, I'm seeing that. They gave me the graph, and you can get the graph yourself. Now it says, oh, you should note that at t equals 1. Let me find what they say if I should know. T equals 1, we get the 0.11. They should note that. Well, let's see if that's true. Well, t equals 1 x would be 1, and t equals 1, that would be 2 minus 1. That's 1. That makes sense. And they say, it says you're going to get a horizontal tangent line there. And that seems reasonable to you. That's a horizontal tangent. Let me just check that out. Is dy dx equal to 0 when t is equal to 1, like they said it is? Well, let's plug it in. It would be 2 minus 2 over 3. It's 0. That should satisfies it. It goes on, it says, you'll also get another point, 0, 0. And I'm going to say, I'm seeing that point over there, but maybe it's not right. Let's take a look at that. So they say that would occur when t is 0. This occurs when t is 0. Let's see if that's true. This would give you 0. That would give you 0. That makes sense. What are they saying? They're saying you're getting a vertical tangent line. So what are they saying? They're saying dy dx at t equals 0 is undefined. A division by 0, so to speak. Undefined. Division by 0. Let's see if that's true. What's my derivative? And again, we're at t equals 0. So we can get 2 on top. And what do you get on bottom if t is 0? You get 0. Yep, as it says, we're going to get that. All right. So I want to point out second derivative, a bit more tricky. Did we do the second derivative for that guy? We did. What's second derivative? It was 2t minus 4. I don't want to go through that nightmare again. 2t minus 4 over 9t5. Let me make sure I got that right. Yeah, I did. So it says, basically, I'm going to analyze that second derivative for t's now. All right. So, and again, we'll look at the picture. The reason for the pictures is the pictures really are helpful. This is second derivative, and I'm looking just at the t's. So, what are the values? I'm going to say t is 0 is one of the values we have to look at because we have a problem on the bottom at 0. It's going to change sign. What's the other one going to be at? What's that number there? That number there is going to be 2, right? So let's take a look at this. I'm going to see what the sign of the second derivative is, between t, these are t values, between 0 and 2 is 1. So let me plug the 1 in. What do you get? You definitely get negative. So concave down. So between 0 and where t is 2. Now someone says, where's t is 2? Do you remember t was 1 here? So 2 is going to be over here somewhere. So what are they saying? They're saying it's concave down until we get up to t is 2. I'm not sure exactly where t is 2 is going to bring me to, but I guess I could figure out that point now, couldn't I? So when t is 2, it says it's concave down, right? What's the point at t equals 2? Well, the x would be what? It would be 8. That's not so bad, right? What would the y be? Well, it would be 2 times 2 is 4, minus 4 is 0. Now, I don't see that in the picture. So I'm going to say is over here somewhere that this is concave down until it gets to that point over there. What is that point? It's 8, 0. All right, concave down. All right, let's keep moving. Let's go beyond the 2. And what's a good number after 2? 3. Plug it in. What do you get? Positive. So what do I know? After 2, this thing goes concave up on me. All right. Let's go below 0 for the t. And what's a good number below 0? Like minus 1. What do you get in top? Negative. What do you get in bottom? Negative. Concave up. Concave up forever over here. So I'm going to say concave up over here. Concave up. All the concave up over there. All right. Let's just read it. Make sure we got that. It says it's pretty easy to analyze. Yeah, maybe. We can see the sign changes t equals 0, t equals 2. We did that. Simple sign now shows that a curve will be concave up. I'm sorry, concave down between this. I did that. And the other points would be 0, 0, 8, 8. Yeah, we did that. We got those points. All right, we did all right. Let's keep going. Oh, we're at the end. So what does that mean? We need to start doing examples now. Let me just recap. Parametrics, hard to understand. What are we doing? We're converting to Cartesian initially. Then what? We need to be very careful about how the relationship between Cartesian and the parametrics. You know, you can get tricked sometimes, right? So you always should look at the parametric form first. So then when you look at the Cartesian, if it's easy, graph it, but please look back at the parametric. Some graphs are tough to construct. What I recommend using software. I really do recommend that. All right. Then what do we have? We have derivatives. I want to point out the derivatives, kind of new to most people, but the derivative dy dx should not be new to you. But in parametric form, what is going to be? Well, it's going to be the derivative of that, the x problem. I'll write this down as x prime with respect to t. Oops, sorry, I got that backwards. It's going to be y prime, the parametric form. That's dy dt. I'll write that down for you. And the bottom would be x prime, and that's going to be dx dt. That's fairly simple, and we derived that. What's the other one we derive? Second derivative, kind of hard to remember, by the way, I'll be honest with you, at least for me. What's that going to be? The dx dt, and the top is going to be the d dt of the prior one, which is the dy dx. All right, you got to get the first derivative before you get the second one. Again, this stuff is in your notes. Take a look at it. We need to move on to examples. After we finish examples, you need to try on your own by doing your own examples, and that is you start doing homework. Thanks for your attention. Again, if you have any concerns or issues that need to be addressed, please come by during office hours, and I'll be more than happy to help you.